forward, which is that we have this big library called ArkLib. In fact, as I'm going to say in a second, we have 5 libraries, which we collectively refer to as ArkLib most of the time in an abusive language. And we're starting to have some interesting stuff in there, which I think is relevant to people who do form verification, but also people who do just protocol specifications and theory and implementations, and maybe the wider community that's here at ZKProofs. And so we had the idea that we should maybe try to have a day that's focused on this and on going over all of this in detail, since there turns out to be quite a lot of content to go through. And the context of all of this is obviously that at the EF we're trying to formally verify all of these ZK VMs, which was talked about last year at ZKProofs and talked about in many other places. And for the cryptography track in particular, for that project, the idea was to be able to verify specifications, proofs of security, and implementations of the proof systems that we use in ZK VMs. And that includes, obviously, Fry, where all of those things everyone knows, and then in the long run, and I'll get back to that a bit later in this talk, obviously trying to bridge the gap from specs of single protocols to specs about the big proof systems that people actually run in production. And the core part of this track is this ArkLib library, which has been on GitHub now for well over a year, which was started by Kwong, and then which became a core part of the project. And now I think we have 30+ contributors on GitHub. Half of them are probably AI, and a nice group of kind of 9, 10-ish kind of core contributors. So as I said, ArkLib is really 5 libraries. ArkLib is the main one, where you have specification for snarks, and you'll find specs for things like Fry. But to actually be able to specify Fry, it turns out that you need quite a lot of things. And so we have, at this point, 3 foundational libraries. One of them is new as of yesterday. So VCV.io is probably the main one. VCV.io is where we have all the abstractions for things like oracles, which you need to do modern cryptography, and which turns out to be nailing what an oracle is and trying to specify what an oracle is to be able to support rewinding and caching and logging. And all of these features that you see in papers turns out to be fairly involved and require quite a bit of syncing. And in our case, it took a few iterations. And VCV was started by Devin, who will talk a bit about this later today. We've got Polyfun, which is a new library out of from yesterday, which is all about polynomial functors. And whether you think that fun is up to you. And interactions, because for all of these protocols, even a basic ZKProof protocol, you have 2 parties and you need interactions, and you need to think about how to model these interactions. So now we have one library for this, and the interaction framework, I think, is actually generic enough that it should be able to do maybe MPC, maybe distributed protocols more generally. And then we have another library again in terms of foundational stuff, which is that we have a fork of Iris Lean, where Iris is a separation logic framework that comes from the rock world, and that's been around for many, many years. And in that fork, we're trying to implement Bluebell, which is this program logic, which I guess Julian will talk a bit about in a second. And this is all to help us reason about programs in a nice way, and particularly in an ergonomic way in terms of doing proofs, so that we can actually start to do nice proofs. And then with all of this, we can actually define specs and security proofs in ArkLib. So there we have Fry, we have specs for all of this, we have security proofs for all of this that we're working on, and then we also have all of the mathematical prerequisites. We heard a lot about proximity gaps yesterday, and we have all of this in there. And I mean, ArkLib, obviously, Julian will talk a bit about the IOPPs that we have in ArkLib. Tobias will talk a bit about KZGs, an example, and then Katie will talk about all of the mathematics that's in there, because most of the library at this point is basically actually coding theory. And then the other nice thing is that we then have another library called CompPoly, which has a formalization of polynomials which are computable, and where we're trying to have efficient algorithms that are implemented. And the idea there is that this allows us to turn our specs into executable specs that you can actually run. We want this for several reasons. One of these is to be able to test the specs. One of these is to be able to do differential testing against the specs without doing the full gamut of form verification. And in the end, actually, the other reason is that we might want to actually run this in production. And I'll get back to this. The idea is that obviously at the end of the day, we want to specify things, we want to prove things, we want to formalize all of these things in Lean. But the end goal is really to be able to say something about production code and say something about code that's running in production. We're looking at several different avenues for this. We're doing 3 in parallel. One of these is just extracting Rust code that already exists via tools like Hicks or Neas, and both emerging, so the difference is a bit moot at this point. This is something that you'll hear about a bit later today with Derek's talk on CompPoly. The other things that we could do is obviously just write assembly. It turns out there's already a project writing an EVM in assembly, and we could do the same for things like verifiers and fairly small scoped programs. And then, of course, we could think about just compiling directly from Lean into a production code that's fast and efficient and formally verified. And this would most likely involve skipping Lean's runtime execution, so most likely this is going to involve just writing a compiler. There's a stand-in there, which would be MLIR, because we have MLIR re-implemented in Lean. And same for RISC-V, this is a stand-in. For a verifier, you might want this to be WASM or x86 or something else. But the end goal is to try to get ArkLib into production, and this is maybe something that will be touched on today, but maybe also something that we'll get back to next year as we first have to finish writing specs and making them efficient and computable and having some prototype verification of some of these. So there's a bit more that I want to say now generally beyond the basic architecture of what ArkLib looks like as a project. And one of these things is obviously that we started ArkLib in 2024, late 2024. And at that time, we were still doing a lot of things manually, but we thought that it was worth doing because Lean has this kind of huge ecosystem of mathematicians who contribute to MathLib. MathLib now has about 2 million lines of code, which is quite a lot, and covers, I think the tagline is that it should cover all the material you'd find in an undergrad course in mathematics, except coding theory, as it turns out. But we thought it was kind of interesting that mathematicians were contributing millions of lines of code to the Lean ecosystem, and computer scientists at that point were not contributing that much. Now there's a CSLib, which is only getting started, and there was nothing for cryptography, there was nothing for reasoning about programs. A lot of things were kind of lacking. And this was kind of strange, because obviously we're computer scientists. In many ways, snarks are actually a very interesting use case for form verification, because you both have interesting mathematics, you have interesting proofs, you have $1 million prizes for conjectures, where you might want to be able to check that something that you get out of these solutions to conjectures actually hold up. And then you also have specs, which are quite hard to reason about, because you want to be able to compose specs, and you want to be able to compose protocols. You want to do some arbitrary number of sum checks, for example, or you want to be able to plug in lookups for different parts, and you want to be able to build a big kind of proof system that you would have in production. And then obviously you have quite a lot to do when you want to then finally verify some actual code that runs in production. And this used to be very laborious. It used to take a long time to do. It used to take maybe many people to do. And we got started on this nonetheless. But then we were very lucky, and lucky is, well, we kind of knew the AI stuff was coming, and we were very much banking on it. So thank you to the AI people for delivering. But in the past couple months in particular, we've had a lot of changes, which is that AI has become very good. AI went from, we can use it for a few things, we can try to play around with it, we can do simple proofs with it, to now we can do quite complicated proofs with it. In fact, like, I guess there's not that much manual proving that's left to do in many cases. And so we've seen a lot of changes to the economics of developing all of this, and that has an impact on the speed of developing all of this. So we've seen a lot of increased automation in our work, both with AI and I think classical automation as well, better tactics in Lean and things like this. But also it's made it much easier to run a library, in the sense that it's much easier to trust contributors to your library when it's in Lean. So we doubled, roughly speaking, our number of contributors in the last couple months. Most of them generate PRs, which I'm pretty sure are 100% AI. Actually, the replies that they give to your comments on the PRs are pretty much AI as well, as far as I can tell. But nonetheless, actually, some of the content ends up being quite good. And reviewing all of this is much easier because we can obviously trust, one, that the proofs are correct, which removes quite a bit of the review burden, because we just need to check statements. And two, obviously, even when we need to check statements, because we have access to all the reference papers, thanks to all the cryptographers to write nice papers, we're able to actually kind of also use this to review PRs quite a bit, and doing the diff between a statement in Lean and a statement in a paper is become much easier as well, and AIs have gotten much more trustworthy at this. So we still have some manual work to do, but all of this has gotten much better, and there's also an exciting time in that sense. And what this has led is just community growth around Lean in particular. So one of the very nice things is that adopting Lean now is much easier. You don't need to learn, the concrete syntax on day one. You can start trying to prototype things in Lean very easily and getting some intuition for how things work in Lean. And this means that we've been able to leverage a lot more domain expertise, I think, over time, both in ArkLib and in other projects. In the sense that now, if you want to say you're a cryptographer and you want to do things, you can maybe just auto-formalize things. And we've seen this. There was a talk about this yesterday with Yoichi auto-formalizing the simplified round-by-round standards of Fry at ZK Summit. Obviously, the Veil presentation by Ron mentioned auto-formalization. And this is kind of exciting as well, that people are able to start doing things very, very easily. A lot more people, therefore, excited about Lean, and a lot more people are therefore excited about contributing. And this has been quite a big help to us in many, many ways. And I think I wanted to kind of bring this up because it means that it's also an invitation for people to come and contribute and participate without necessarily having to do, like a 6 months Lean bootcamp at first, because it's now much easier to jump in and prototype and see how things work and maybe do something useful very, very quickly, whilst you also obviously learn things in parallel. And we've benefited from this with the Lean ecosystem growing, because a lot of the problems that we have or that we thought we would have end up not being problems because someone else that we've never heard of tries to solve it and manages to solve it, and vice versa. I think we've actually had quite a few tools that might be used for other things. So some people doing AI for mathematics are excited about our computable polynomials. Signal, which is being formally verified now with the Beneficial AI Foundation, are using VCV, most likely, we hope. And so the Lean ecosystem is growing and being incredibly helpful, and is growing especially in terms of adding domain expertise from different fields and not just people who have a pure form verification background, which has been a very nice thing. In particular, so to touch back on proving with AI, since that's been quite a big deal with ArkLib, I have a picture here of when I did the proof of Polishuk Spielman in January this year, which I think was the first kind of meaningfully or interesting proof that we did in ArkLib, right around the time that the models just kind of started getting much better. This was the times of Opus 4.5 and GPT 5.3 or 5.2. And this was done with logical intelligence. And so we'll hear a bit about this as well. So logical intelligence have some people who we're very lucky are here today, and they'll talk a bit about all of the AI stuff. But this has been really nice, right? So you can take Polishuk Spielman, suddenly proving it by hand the first time for humans, I'm going to say, took a bit of time. It's a valuable kind of contribution, and it was part of a PhD in the 90s. And then obviously the proof there was broken. And then Ben Sasson and his co-authors had to fix it in the proximity gas paper. And then I could just come along, write down an outline of the proof, write down some hints you can kind of vaguely see there on the screen that I did myself. And then I could give it off to the AI, and then the AI could do it. And this took about 8 hours and $200 worth of compute, which is roughly an hour of industry contractor time within those bounds. And so something that would have taken certainly more than 8 hours to maybe formalize by a human expert now is much, much easier to do. And so we're able to kind of really scale things. And one of the nice things is that this means that if you look at papers that come out now, and you look at what we have in ArkLib, and we have all of the foundational coding theory and things like this, and someone adds maybe one more theorem, stating it and being sure that the statement is correct is maybe not too much trouble, right? It can be just one statement, maybe 2, maybe 3, very tractable. And then proving these, especially if we have access reference proofs, becomes much nicer. You offload it to the AI, you obviously have the pen and paper proof to get some intuition and some sense of how the proof works, and obviously for your own understanding, which is still important. But you can quickly kind of get this added into your library and iterate very quickly. And this means that if new cryptography comes up, then hopefully we won't actually lag behind, which has traditionally been an issue for form verification. So this is one of these very exciting things. But then obviously it comes with a big caveat, which is that for proofs it works very well because the Lean kernel gives you some assurance about the proofs. For specs it doesn't work that well because it's very easy to have specs that are slightly off. And so there needs to be a bit of a slight warning sign here. Because we've seen obviously some things not go well when we've tried to use AIs for some things. I think Kwong in particular will talk maybe a bit later today about some examples of this recently, that in some ways you can maybe generate a categorical model of the UC model, and that kind of works out, and some other things that should be maybe simpler don't work out at all. So there's still quite a bit of care that needs to be taken about anything that isn't actually checked by the Lean kernel. And this is also a bit of a maybe a bit something to take into account with auto-formalization, that some of the auto-formalizations we've seen have proximity generators which are axioms, oracles which are vectors of n elements, and things like this which are maybe fine for specific use cases, but maybe not general enough, and maybe certainly not capturing the abstractions that you have in the cryptography literature in the right way. And so we kind of want to take care maybe highlighting this and not being kind of too overexcited about the AI stuff in general, even if there are things where obviously it's just solves an entire class of problems. The other things to say about specs is obviously that specs can be kind of tricky to get right, because for cryptography, the specs are quite live. So with Fry in particular, Fry has been around for nearly 10 years now, since the original paper. And it's gone through many changes in terms of how people implement it, in terms of the fields that it works on, but also in terms of the protocol itself. There's been a lot of optimizations and different ways of thinking about it, and implementations have evolved quite a bit. And so if you want to write specs that actually map to implementations and map to the kind of modern understanding, you can't just stick to the papers. And that turned out to be an interesting thing for Fry, which we had to go and do things in a slightly different way. We had to make it fit with the interactive alcohol reduction framework that we have in ArkLib. We had to go and talk to cryptographers to validate this. I think Albert Carretta played quite a big role in validating that we weren't doing something stupid. And so that's another part of doing specs, which is you have to do specs in a way that is kind of smart, both for the use case for your specs, whether that's verification, whether that's just doing security proofs, whether that's something else, and in the way that you obviously validate your specs and then try to get good proof ergonomics to prove things against your spec. And I guess that'll be somewhat part of Julian's talk later in this session. The other thing that you need to remember is to try to keep track of everything. Dara is not in the room, but she would otherwise recognize this this slide. So this was an attempt that we had at Hicks earlier this year to try and understand everything that would need to be verified to actually get an end-to-end proof for something ZK. We split 8 people into 2 groups of 4, and then we did it in parallel. The first thing you'll notice is that both things do not look the same. And so if you stick 2 groups of 4 people, they won't actually do the exact same thing, at least in terms of the organization. The other thing that is harder to notice on the slide, because the slide is unreadable, and that's somewhat part of the point, is that actually both of them have things that are missing. So both of these things don't overlap entirely. Both of these have things that the other group forgot to do. Now, we were bounded by time, obviously, when we did this. But it's still an interesting point that obviously it's quite hard to still come up with the entire list of things that you need to check. Now, some of this goes beyond the bounds of ArkLib. You have things like the guest program, the application protocol, and things like this, a part of this sketch. But obviously, at some point, you do want to connect things, right? And so we'll also hear about front ends for that reason today at ArkLib Day, and then part of the work in the coming year will be trying to connect these front ends to ArkLib and to have a proper front end and back end integrated system where we can actually think about doing end-to-end proofs and try to grow the scope of what we verify as a whole, and rather than having everything be separated and isolated from everything else. So this is, this was quite a fun exercise, and then I've used it ever since on slides, and we've definitely found that the scale at which you need to verify things, even for a proof system, let alone an implementation, is quite big. The reason for this is, as I said before, the proof systems that we see now in practice are much more complicated than just one protocol. But also because at the scale at which ArkLib is, I think, which has probably in the hundreds of thousands of lines of code at this point, I would say, you have a lot of specs of code. Given 1,000 lines of code, you typically expect bugs. I think the measurements are usually that you have between 1 and 50 bugs per thousands of lines of code whenever someone's tried to measure this, regardless of the language. And 1 bug in 1,000 lines of code is considered kind of, whatever, top tier NSA military, high assurance grade or whatever. And so if we have pushing 100,000 lines of mathematics and specs, it's very likely that there are at least some statements there which are slightly off. We do find statements which are slightly off every time. Actually, Polish experiment, we got it wrong twice. So that's another thing to try to keep track of, which is that we still need to obviously validate that the statements that we prove are the correct statements, that the specs that we have model the correct protocol that we think it's modeling, and that we actually can check what we have. And that's another thing to obviously take care of, especially if we start using AI to write more specs, is keeping track of what we're actually doing, and keeping track to just doing what we actually need to do to verify what's in production, if that's the end goal, and not just have things that we can say are proven in Lean, which might not actually be that relevant or interesting, or be slightly off. And we've seen obviously errors of formally verified code, or claims of formally verified code, which turn out not to hold, because the spec against which something is formally verified actually has some things that it's not checking. So that's the main last point that I wanted to bring up, and that I think we'll keep in mind during the day. And then, so that's the schedule for today. Yeah.
Do you keep track of that anywhere else than this slide? Is there an outcome of that work that is captured elsewhere?
I mean, we do like reviews in ArkLib.
But this graph that you're presenting.
Oh no, this is just for the.
There's no like mega map that came out of it.
No, because none of these turned out to be good enough to be final. I think one of them forgot Fiat Jamais, which is a bad one to forget, and then I think the other one forgot. I can't remember. But I mean, so one of the interesting things about this as well is you'll notice this for one is that soundness is much easier. I think that's an interesting point. Soundness is much easier than completeness, in the sense that completeness you need to verify far more things, because soundness has a kind of adversarial thing built into it, which is that the honest verifier has to be resilient against like a malicious prover, and a malicious prover could be like a prover with a buggy compiler or whatever. So soundness is kind of okay, and then completeness is really hard, because completeness you have like 4 different, I mean in a ZKVM you have 4 different compilers. You compile the guest program, you compile the constraints, you compile the witness generation, you compile the verifier, you compile the prover. Some of these compilers are the same, but you have probably at least 4 compilers, if not more. And so that's part of the stack being huge, and that's part of the trust in code base. Even if you verify like your protocol and you verify that the verifier is the right thing, if the compiler fucks you up, then that's it. I don't know if I'm allowed to swear on the stream, but yeah, like the slide shows many things, and it's actually not complete. And like I said, one of the interesting things was that both don't show the exact same thing. Certainly not in the same ordering, and certainly not with the same connections between the components. And then you have all the interfaces for precompiles and things like this, which right now are not like entirely specified. And so the range of things that you actually need to check to get an end-to-end proof of like this implementation of this very complicated protocols with some checks and WIR and log-up GKRs and other things is pretty tough. And then you obviously need to connect that to the arithmetization and whatever thing is being arithmetized, and the witness generation and all of this. And so one day maybe we'll have a complete outline. But obviously, so far we don't. And some parts as well, we don't know what to do, right? So recursion is, we need the cryptographers to also help figure that one out. So recursion, not entirely sure what exactly is the notions that we want to formalize to be confident about our formalization recursion and be confident about formally verifying some recursive proof system. And so that's, there's still many to-dos and still quite a bit of things to go through. But we'll start obviously at least discussing many of the things that we want to go through with today. And so we'll have a fairly simple schedule, which is that we'll look at some examples of protocol specifications. We'll start with KZG. Tobias actually presented his KZG formalization Isabel last year's ZKProofs. And so this year he's talking about KZG and Lean, joining the winning side. And then we'll have a slightly longer talk, obviously, reasoning about IOPPs. And so Julian there has worked on Fry and WIR in ArkLib and trying to specify them and trying to work on program logics to reason about all of these things. And so we'll see a bit about this. After that, we'll have, I guess, a coffee break, and then we'll have a bit more about the foundations of ArkLib to maybe get a better understanding of how the IOPP specs work. So the one main thing here is VCV IO. The paper for VCV arrived on preprint today at 6 a.m. So that's, you can look at the talk and then you can look at the paper. But there are interesting things there. So, it turns out that oracles are the free monad over the polynomial functor. Devin, I guess, will explain that in more detail. Devin is shrugging. But it's self-explanatory, yeah. Your Turing machine tape pauses to do the oracle query. That's an algebraic effect. That's all it is. But it turns out that specifying oracles is not easy, right? Once you want to do like things properly and you want to think, okay, cryptographers want these features out of oracles, they want things like rewinding is a pretty core thing to have. Then you need to have oracles which are not just like a vector of answers to queries or something like this. You need to try to model things properly, and that turned out to be quite a long quite a long effort. It took several iterations. And that's something that you won't get from auto-formalization, because if you try to auto-formalize a single paper, you're going to get your paper, you give it to your AI, it's going to take the SERM statements that are in the paper, and it's going to write something down that seems plausible. But obviously, it's not going to one-shot a formalization of oracles in all their complexity, because that's not described in the papers, it's just assumed. And same for more broadly, like the interactive oracle reduction framework that ArkLib is based on to specify protocols isn't something that's described in a paper somewhere. It's something that had to be done independently by Kwong and Devon, and took quite a bit of work, and has some novelty to it. So we're not actually just taking cryptography off the shelf, rewriting it in Lean. There's a bit of thought that actually has to go into how to do this properly, and that's also, I think, part of the point of these kind of foundation sessions is to try to understand this a bit better, and to try to maybe also communicate the work and maybe some of the limitations of not doing this, and not being able to model what cryptographers exactly want, and then potentially having gaps that come back to bite us in the end. So we'll hear about VCV. We'll hear about computable polynomials from Derek, which is the ComPoly library. There was joint work between ZK Security with Gregor, and obviously Nethermind with Julian and his colleagues, and then Derek more recently when he joined EF, where they were trying to have efficient field arithmetic in the end, and we're doing things like efficient decoding algorithms, and generally speaking, kind of any FFTs, NTTs, and all the computational stuff that you want to be somewhat efficient and fast, both so that we can actually verify what people are doing in production, but in the end also that we can think about making this fast enough to be in production. And then we'll hear about mathematical foundations. I guess this will be a good complement to some of the proximity gap stuff that was discussed yesterday, if you want to see how this ends up looking in Lean. And in particular, there'll be a mention of the paper that's presented right after lunch in another room on polynomial generators that we're doing in parallel to them presenting it, or presenting it before them, and formalizing it, at least started formalizing it before the paper ever got presented, which is kind of nice. Then we'll do front ends after lunch. There are several teams which have been building front end DSLs in Lean. This should be fairly self-explanatory. Circuits, we all know circuits. They're great. They're full of bugs. We should try to clean them up. No pun intended. And at least that kind of goes some way between bridging ArkLib to concrete things as well. And then the last session we'll have will just be first a talk by Kwong on evolving foundations of ArkLib. Kwong unfortunately couldn't be here today. He'll be remote, but he's been doing a lot of exciting work in the recent couple weeks after Layer 0 freed him from optimizing all of their Rust code. And then we'll obviously finish off with some simpering with AI, since, like I said, we've been using logical intelligence tools quite a bit to get a lot of proofs, certainly I have, and so that way I think it felt like a good time to actually have a discussion and a presentation of people who actually work on these tools to help us all understand it better. I think that's basically it for today. I tried to keep it short enough so that we can do the changeover and not run too late with the other talks, but I think we have maybe a bit of time for questions, and then we can do the switch over in parallel.
I guess let's start the day.
Oh yeah, that's fine. Out of moment of doubt. Perfect. I'll get his slides. And so that way, because you have quite a bit of slides, so that's what you might need.